In this video, you will learn how to factor a sum and a difference of two cubes. So starting off, we're going to start with what is a perfect cube. Okay, so I have perfect cubes. So that's when we have 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, 7 cubed, 8 cubed, so on and so forth. So if I look at it, remember a cubed, if I have 1 cubed, it's 1 times 1 times 1. Okay, when I multiply that together, I get 1. Okay, I'll do it again for 2. I have 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So 8 is a perfect cubed. 3 cubed would be 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. And last but not least, 8 cubed gives me 512. Now, we're used to dealing with cubes as numbers, but we also have perfect cubes that are variables. Okay, so perfect cubes that are variables are multiples of 3. So I have x cubed, x to the 6th, x to the 9th, x to the 12th, and so on and so forth. Now, when understanding this, we also have to understand the inverse, okay, the opposite. So we're used to taking the square root of things, but now we're talking about cubes. So we're going to take what is called the cube root of things. So what that looks like is I draw my little radical, but now I have what is called an index number above the little tail of the radical. Okay, so the cube root of 1 is 1. So we're just doing the opposite. The cube root of 8 equals 2. The cube root of 27 equals 3. The cube root of 64 is 4. Cube root of 125 equals 5. The cube root of 216 is 6. Cube root of 343 is 7. And the cube root of 512 equals 8. Now, if we're talking about the variables, it also works the same way. So I have the cube root of x cubed. Remember that cube cancels out that cubed. The index cubed and the exponent cubed cancels each other out. So I'm just left with an x. Well, now, if I have the cube root of x to the 6th, I can't just have an x. I would have 2 x's left over, so I have x squared. Okay, the cube root of x to the 9th equals x cubed, and the cube root of x to the, not 12, the cube root of x to the 12th would be x to the 4th, and that pattern continues as you go on with multiples of 3. So now, let's get into actually factoring a sum of two cubes. So here is our formula. Okay, this is very important to know. So this part, the first part, a cubed plus b cubed, is telling me that I have some number or variable cubed plus, hence the word sum, and why we have a plus, some other number cubed. And this is how it's factored. So this is the factored part, right here, factored. So let's start with something relatively easy. So let's start with example 1. Let's do a basic one. So we have x cubed plus, let's do 512, since that was one of our perfect cubes on the other side. So what I notice is x cubed is perfect, 512 is perfect. Again, that's from the previous slide. How I do this is first I determine, okay, there's a plus sign, so I know I'm doing a sum of two cubes. So I know I need to use my a plus b times a squared minus a times b. So again, these are being multiplied up here, plus b squared. Okay, so my signs are plus, minus, plus, opposites. Awesome. So what I do is I identify my a. So if I look in my formula right here, my a is the first term. Well, what's in that place is the x. So how I determine what a is I do the opposite and I take the cube root. So again, the cube root of x cubed is x. Then I notice my second term is in the spot where b is at, and it's being cubed. So to undo that, I take the cube root of 512. Well, the cube root of 512 is 8. Now all I'm going to do is plug in x and a anywhere I see an a and a b. So if I see an a, I'm putting an x. If I see a b, I'm putting an 8. So I have a plus b, so my a is x. My b is 8, so I have x plus 8. Now, my next one I have a squared, so I take x and I square it. So when I square x, I get x squared. Now I have minus and a times b, so I'm taking x times 8, I get 8x. And then I'm going to square b. So 8 squared is 64. So this is the factored form, and there's nothing else I can do, and I leave it like that. Okay, so let's do another example of a sum of two cubes. So looking at example 2, now I have 4x, and that should be to the 4th power. I'm sorry, it made a typo. So this should be 4x to the 4th plus 8x. There we go. Now, if I look at this, I notice 4 and x to the 4th, those are not perfect cubes. Okay, and 108 and x aren't perfect cubes, but I look and I notice that they have a GCF. Okay, they do have a GCF, and so I got to make sure that I look for GCFs first, because if I don't, I can't solve the question like I'm used to. So I noticed that they're both divisible by 4 and they have an x in common. So I have to factor that out before I'm able to do my sum of two cubes. So again, I divide by my GCF, and since it's my GCF, it goes out front. And then I write down what I'm left with. So I get x cubed plus 27. Well, now I look, x cubed's perfect, 27's perfect, so I can use my formula, and I'm going to write that off to the side. That way I have it for reference. So again, it was a plus b times a squared minus a times b plus b squared. This is something that will need to be memorized. Okay, so now I need to identify what a is and what b is. So let's start with a. I take my first term for a, so the square, or the cube root, not the square root, the cube root of x cubed is x, and then I take the cube root of my second term for b. So the cube root of 27 is 3. Anywhere I see an a, I plug in an x. Anywhere I see a b, I plug in 3, and then I simplify. So it says a plus b, that is x plus 3. And then I have a squared, so that gives me x squared. A times b would be x times 3, which is 3x. B squared would be 3 squared, or 3 times 3, which is a positive 9. And then I can't forget that I had a GCF out front, that 4x. And this would be my factored version of it. So I still did a sum of cubes, but I made sure I left my GCF out front. Okay, one more example of a sum of cubes. This example, notice that I have 8 plus x to the 6th. I am not going to rearrange it to put it in standard form. They gave it to me out of order, so I'm going to keep it how it is. And I'm still going to do the same thing. Again, I notice I have a sum. Okay, so again, a sum. So my formula is a plus b times a squared minus a times b plus b squared. Oh, forgot the 2. If I look, I always look for a GCF first. So 8 and x to the 6th, there's no GCF. So no GCF on this one. Let's go from there. So now my a is in the first spot, so I take the cube root of a. The cube root of 8 would be 2. And then I take the cube root of my second term for b. So the cube root of x to the 6th would be x to the 4th. Not x to the 4th. Ugh, silly Miss Farina. It would be x squared. Okay, and now I plug it in. Anywhere there's an a, I plug in 2. Anywhere there's a b, I plug in x squared. So now, a plus b would be 2 plus x to the 6th. A squared is 4. A times b, so 2 times x squared would be 2x squared. And now, a little more challenging, we have b squared, which would be x squared squared. So if I do it like that, there's 2 ways we can look at it. I can look at it as I have x squared times x squared. And when I multiply, I add exponents, so I get x to the fourth. Or I can remember my exponent properties. Okay, exponent properties tells me if I have an exponent raised to an exponent or a power raised to a power, I multiply. And when I multiply 2 times 2, I still get x to the fourth power. So I'm going to plug that in right here, x to the fourth. And this would be the factored form of this equation. Okay, moving on to a difference of two cubes. So this is very similar to the sum of two cubes. The only difference is now that we have a difference, which means we're subtracting. So I have something cubed minus something else cubed. And this is the factored form. This is, again, very similar to a sum of cubes. The only difference is the signs. Now it goes minus, plus, plus. So let's start off with an easy-ish example. So example 1, let's start with, let's use the variable b cubed minus 1. And I know some of you are like, oh no, she's using 1. Yes, you can use 1. It's okay. It's not going to hurt. So I do the same process. The first term is my a. I take the cube root. The cube root of b cubed is b. If I look at 1, 1 was in my perfect cube list. So I take the cube root of that for b, and I probably shouldn't have used the variable b. So I'm going to go ahead and change it. Let's use a different letter so we don't confuse it. Let's use the variable, pressing all these different buttons. Let's use the variable c. That way we don't confuse it with this. So c. So a equals c. Then the cube root of 1 is 1. And now all I do is plug it into this. So a minus b, I get c minus 1. A squared would be c squared. A times b is plus 1c or plus c. And then plus b squared. 1 squared is just 1. So this would be the factored form. Okay, looking at example number 2 for a difference of cubes. I look and now I see that I have 2x to the 5th minus 16x squared. Again, now I notice, well, these aren't perfect squares, which means I have to check for a GCF. So my GCF in this equation would be, let's see, 2 and x squared. So 2x squared. So I'm going to divide out at 2x squared and see what it leaves me with and see if I have a difference of cubes. So my GCF goes out front. 2x to the 5th divided by 2x squared gives me an x cubed, which is good. That's a perfect cube. I still have a different sign, so I'm subtracting. 16x squared divided by 2x squared is 8. So now I have a difference of cubes. So I go through the same process. I'm going to go ahead and write my handy dandy little factored formula for me. So a minus b times a squared plus a times b plus b squared. So a, to figure that out, I take the cube root of the first term. So the cube root of x cubed is x. The cube root of 8. Cube root of 8 is 2. I plug and chug. A minus b would be x minus 2. A squared is x squared. Plus a times b would give me a 2x. B squared would be 2 squared, which is 4. And then I can't forget my GCF, and it hangs out with us. Okay, so I have one more example. This one now has two variables. I still look for a GCF. I notice, x and y, they don't have anything in common. 8 and 3, or 343, there's nothing in common. So there is no GCF. So I notice that it's a difference. So here's my difference formula. Right there. Okay, so I take the cube root of the first term for that. So a equals, the cube root of 8 is 2. The cube root of x cubed is x. Okay, and then I take the cube root of the second term. cube root of 343 is 7. The cube root of y to the 6th is going to be a y squared. They try to get me with that one. And now I just plug it in. So a minus b. So a is 2x minus b is 7y squared. Okay. Now I have a squared. So remember, a squared. Oops, I put 2a. Silly me. So a squared means that I have 2x times 2x. Okay, 2x times 2x is 4x squared. Or I remember that I have to make sure I distribute that exponent and I get 2 squared and x squared, which gives me the same thing, 4x squared. I can't forget about the 2 squaring it. So either way I go, I get 4x squared. So 4x squared. Then it says we're adding a times b. So 2x times 7y. Well, 2 times 7 is 14. The variables, I just do x, y squared plus b y squared squared. Let's see, I have 7y squared, and then I'm squaring it. Well, again, I got 7y squared. That looks like a 2. That's a squared. Times 7y squared. 7 times 7 is 49. Y squared times y squared. Remember, when I multiply variables with the same base, I add the exponent. So 2 plus 2 is y to the 4th. So I get 49y to the 4th. And I had no GCF, so this would be the factored form of that for a difference of cubes. So it's important that you know these. This is a really important concept. There could be a mini assessment coming up, so just be prepared for it.